Now, there are some other terms that are going to help us while exploring our data. These is what we call variation. So the variation is the tendency of the values of a variable to change from measurement to measurement. So, we don't expect everything to have the same value, right? If you're measuring the height of people, it's going to change, right? There's going to be a range of values. You don't expect everybody to be 6 feet tall. Some people might be 4 feet. Some people might be more than 6 feet, right? There's a whole range. And each measurement will include a small amount of error that varies from measurement to measurement. So don't forget that all data sets are essentially measurements, right? They've been attained. That data has been measured and somehow gathered and put into that data set. So part of the variation in the values of a variable might be not from actual variation in the measured object, but from error associated with it. And this error, might be human error, it might be other forms of error, it might be measurement error, but there's always an error component to it, which you should keep in mind. And every variable has its own pattern of variation. And this pattern of variation can reveal some interesting information. And this is also a part of exploratory analysis, right? When you discover something due to the variation of a variable, that's valuable information that you might be able to use, right? That's a good result of doing some EDA. The best way to understand that pattern is to visualize the distribution of the variable's values. So we learn how to visualize single variables. We learn how to visualize two variables on a single plot. All of that in the visualization section of the last part of this course using ggplot2. So now you can just take individual variables and you can plot them and you can view their distribution and ask questions based on, the distribution. Why does it seem most of the values for this particular variable are like clustered on the left side or the right side, or why is the distribution shaped like this? And, all those type of questions you can ask and you can answer. Now, it's also very important to understand what different types of variables are. So there are different types of variables, and the methods you'll be using or applying to the different types of variables in order to better understand them through your EDA process will differ based on the type of variable. So like the main two categories would be categorical variables and continuous variables. Categorical variables are essentially those variables that only take on a very small set of values. If you remember from the first part of this course, when we went over factors or even character vectors, those were essentially for categorical variables. For example, hair color can only take on 3 or 4 values, right? Red, black, and brown, or whatever, right? So 4, red, black, brown, and blonde. Maybe throw in some extra stuff, maximum, right? How many colors is it going to be? The most extreme case. It's a small set of value. It's not a continuous variable. Unless you want to be very specific and go into the exact shades of black and brown and whatever's in between and that kind of stuff. But still, most probably in most practical scenarios, it's going to be a fixed set of values. And so that would be a categorical variable. Whereas continuous variables can take any of an infinite set of ordered values. So, or you're measuring the kilometers of a car, for example. You can have almost an infinite set of possibilities for how many kilometers this car rode, especially when you consider meters within the kilometers, right? So, it could be like 100,000 kilometers and 5 meters or 6 meters, or even 5 meters and 15 centimeters, right? So these are all continuous variables. So you have to really understand the distinction between a categorical and a continuous variable, because the type of plots you'll be plotting in order to explore this data and explore these variables will differ based on the type of the variables being compared or analyzed or explored. Some other values would be unusual values. So these are not types of values, but they're values that you might encounter and you might decide to do something based on. So unusual values can be like outliers. These are values or measurements that seem to be oddly placed, or they don't make sense. They don't fit into the general pattern of the rest of the variable. It just seems like it's either a mistake or just a very unusual case or an exception or something. So you'll probably want to do something based on that, because it might skew your results, right? You might have 100,000 measurements and they all have a general trend, but then one value is way out there somewhere, and it might throw off, the average of this variable. It might throw off the algorithm or whatever. And you might choose to just remove that because, it's very clearly not supposed to be there. But in other cases, right, depending on the problem you're trying to solve with your data, that outlier might be very crucial, and it might be a very big mistake to remove that as well. So that's all stuff you have to keep in mind when you're doing EDA, or more specific, not when you're doing EDA, because either case, it's going to be useful for you to remove it to see the result. But when you're actually doing pre-processing for your model and determining whether or not that should be removed or not, that's when it's very crucial. Another type of value would be, missing values. So there are two options. There are two things you can do when you encounter a missing value. You can either drop the entire row, or you can replace the value with missing value. So this actually applies to both unusual values and missing values. So you can apply these two options to both unusual values and missing values. So if you have an unusual value, you can either drop, the entire row, or you can replace it with something else. And you can do the same thing with missing values. So you can either replace the missing value with something, or you can drop the entire row. So these two steps can be applied to both these scenarios. Now there's something called covariation. So remember, variation describes the behavior within a variable, whereas covariation is a tendency for the values of one of two or more variables to vary together in a related way. Okay, so covariation is more external, while variation is more internal. In variation, you're exploring that variable and what's within it. Covariation, you're exploring the relationships between different variables. And these relationships might be explored differently based on their type, as we'll see now. So the best way to spot covariation is to visualize the relationship between two or more variables. Now, you might say, my data set has 20 different variables. If I were to visualize a combination of all of these, it would just take too long, or it would be very hard to know which of the plots are important. So that's where, this creative process comes in, being able to intuitively grasp possibilities and covariation between different variables and trying them out and that kind of stuff. But in the worst case, it's still very easy to just plot all the combinations. There are even functions that do that for you automatically. And then based on the results, you can look at them. And if you see a relationship, if you see some kind of correlation or covariation, then you can go into more specifics and just plot those particular plots and examine those. Now, the way you would observe or explore for covariation would depend on the type of variables involved. So if you want to compare a categorical variable versus a continuous variable, you can use either a frequency plot or a density plot or a box plot. A box plot is something that, a lot of people are scared of, but I'm going to be explaining that in this presentation. You can explore categorical variables versus categorical variables. And for this, you don't really need to plot anything. You can just create a table and just see, the relationships or the correlations. Or you can compare, continuous versus continuous variables, which is basically what we've been doing in this section so far. And that can be done using, a scatter plot or a line graph or whatever. So depending on the type of the variables involved, you're going to be using different plots. So different geom functions in ggplot2. Now, a box plot is something a lot of people are scared of, and they get confused, and it's very hard for them to understand. And that's why I'm including, this is the end of the presentation of this video, and I'm going to be just very quickly explaining what a box plot is. And I would advise you to refer back to these two slides when we actually do plot a box plot, just so you can compare, you can see the visual, and then you can come here and you can see what each part of the plot means. So a box plot is an alternative to display the distribution of a continuous variable broken down by a categorical variable. So that's where the true value in a box plot comes out. It allows you to compare a continuous variable with a categorical variable. And it's a type of visual shorthand for a distribution of values. So it actually summarizes for you quite a few statistics or metrics about those variables that you're comparing. And it summarizes that data in a single plot. So that's why it's very popular among statisticians, and it has been so for many years, even before machine learning became popular. So a box plot essentially consists of a box that stretches from the 25th percentile of the distribution to the 75th percentile. And this range, or this box, is known as the interquartile range, or the IQR. And in the very middle of this box is a line that might be placed not at the very center, but closer to the top or the bottom, depending on the distribution. And it displays the median, so the 50th percentile of the distribution, right? So if it's located a little bit higher up, that means that the data is skewed in that direction. If it's located a little bit lower, it means that, the center of the data, the median of the data, is located more towards the bottom. So this box, right, gives you a sense of the spread of the distribution and how symmetric it is about the mean, or how skewed it is to one side. Additional to this box are visual points that display observations that fall more than 1.5 times the IQR from either edge of the box. And these are plotted individually because they're unusual. They are outliers, right? They're the unusual ones that don't fit the general trend or the general pattern. And so that's very useful, right? You just see a dot where, there's an outlier. And there are also lines that come, or, some refer to them as whiskers, and a box plot can also called a whisker plot. But they're essentially lines that stretch out from the ends of the box, and they go from the non-outlier point in the distribution and connect all the way to the box. And when you see this, you get a very good understanding, a very good sense or a summary of what's going on in that variable. And we're gonna be plotting our own box plots, and I'll be going over this once more there, visually explaining everything. But if you ever, get confused, come back and look at this slide. And here are some references. There is a chapter in R4DS by Hadley Wickham that we've been referring to up until now called Exploratory Data Analysis. And I'm going to be taking some stuff from that chapter as well. So definitely, if you want some extra material, go and take a look at this chapter. And if you haven't by now, definitely get used to using this book as a reference. This is a very good book for data science using R, especially using the tidyverse. It was written by the creator of the tidyverse after all, right? Hadley Wickham. And then I've also taken some examples from, a Kaggle workbook or a Kaggle workbook, which you can check out here. So I will see you in the next video with some hands-on exploratory data analysis. Thanks. Bye-bye.